In this video I'm going to talk about universal functions. So this is a thing that depends on NumPy, so as usual I'm going to start by importing NumPy. So now let's maybe, to explain what's going on here, let's maybe make a list of angles. Okay, so U is going to be, so we're going to use this np.linspace. Okay, so I'm going to do 0 np.pi. And let's say 100. Okay, so this this gives us a list of 100 angles from 0 to pi in equally spaced. Okay. Remember, this is so this you should remember is the right notation for the number pi in Python. When we're using NumPy, we can do np.pi with a little p. Okay, so now suppose we want to calculate the sines of all these angles. We want to make a new vector v that contains all the sines of all these angles. So maybe the most obvious way to do it is like this. We make a vector of zeros because that's where we're going to store these things, and then we do and then we have a loop I running from and then we're going to do vi, we're going to set equal to the sign of the ith element in u. Okay, right, and now and then we can print v at the end. Okay, so so that worked. I mean, here we are. Here's the list of sines of these angles. So sine 0 is 0, and then kind of somewhere in the middle, you get to around somewhere in the middle here. It's got approximately 1, right? I mean, it's all some slight round off errors, and we actually haven't got exactly pi over 2 in our list, but so we get pretty close to 1, and then down towards the end, this is sine pi ought to be 0. In fact, again, there's some slight rounding errors. We've got 10 to the minus 16 instead of 0. So that worked, but actually it wasn't really necessary to do that. We could just do v as np.sine u. Yeah, this is because v the sine function is what's called a universal function. It kind of primarily just takes in one number and spits out another number. But if you feed in an array of any shape, then it'll just calculate the sines of all the elements in the array separately. So on the first hand, firstly, of course, this is much simpler. We don't have to write the loop or anything, and it's nice and tidy. But also maybe less obvious is that it's actually much faster. Here, we've only got 100 entries. It really doesn't really matter too much. But it is kind of quite common in applications in scientific computing. You might be working with arrays with thousands or millions of entries. And then you do need to kind of be a bit more careful about trying to make things efficient. And I don't really want to get into exactly the design of the internals of Python and NumPy, but you can just take it as given. But basically anything that you do with these kind of universal functions which operate on a whole array more or less simultaneously, it's going to be substantially faster than doing it with this kind of loop, as well as being easier. So we'll get rid of that, and that's so that's an example of a universal function. And most things that NumPy defines are also universal functions. So for example, suppose we want to round all this to 3 decimal places. We can do the function np.round. 3, and the rounding function as primarily is intended to just operate on a single number, but again, it's a universal function. If you feed in a vector or a matrix or everything, it'll just do the rounding separately on all the different entries. And it's actually kind of, we had a separate video about broadcasting, and a similar kind of thing is going on with broadcasting. So let's just do another example of that. So we do np.arange 5. Okay, so let's Okay. And now let's do b is 10 to the power a. So again, what's happening here, you know, we so we do 10 raised to the power of a vector, and Python kind of does the obvious sort of thing. It I mean, 10 raised to a vector itself doesn't sort of immediately mean anything, but we just sort of raise 10 to the power of all the elements in the vector. So we do 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4. Gives us this thing here. Okay, so now we can, as we mentioned previously, we've got these two vectors. Let's actually write it as print b here to be consistent. And two vectors the same shape, and as we mentioned before, in terms of broadcasting, you know, we can just add them together and it will add corresponding entries, or we can multiply corresponding entries, or we could take a maximum of a and b. So again, it will do this element wise. It'll take the maximum of every entry in a with the corresponding entries in b. So although in fact, so you don't get anything very interesting there. Let's do maximum of 10a and b. So then if we do maximum of 100a and b, then you get 100, 1, and 100, 200, 1,000, 10,000. Okay, so so again, that's relying on the fact that this maximum, you know, normally we just take the maximum of two numbers, but if we, because it's a universal function, Python will attempt to apply it in some kind of sensible way whenever we feed in some vectors or matrices or whatever. It will, if you feed in two matrices of the same shape, it will just take the maximum element by element. And if you feed in two matrices of different shapes, then Python will try to broadcast them to make them in the same shape before taking the element-wise maximum. So let's maybe just do a bit more of an example where we can actually time our code and see how long it takes. So what we're gonna do some stuff with random data. So we're just going to do import random as RND. And so we've got this function rnd.random that gives us a random number between 0 and 1. Okay, so now we're going to do a function to calculate the variance of some list of random numbers. Okay, so the first version. Okay, so the n, the parameter n, that's going to be how many random numbers we're going to generate. So let's do the most kind of obvious version with no broadcasting, no numpy stuff, and whatever. So we're going to start with an empty list. And then we're going to add random numbers to the list one by one. Okay, so each time we go through this list, we append a random number to the end of the list. Okay, so now we've got a list of random numbers. We want to calculate its variance. So we've got there's a formula for the variance, which involves calculating the sum of the elements in the list and the sum of the squares of the elements in the list. So sum x is going to be the sum of the elements, sum x2 is going to be the sum of the squares. Okay, so then we have another loop. We go through all these things here, and we're going to do. Well, actually, yeah. So let's do it slightly differently. Let's do for x in L. Okay, so we get the same effect, but as we're going to do a loop over the elements of our list, and then we add x onto the sum of the x's. And we add x squared onto the sum of the x2s. And, and then the mean of the x's is just going to be the sum of the x's divided by our n. And the mean of the x squareds is going to be the sum of the x squareds again divided by n. The standard formula for the variance. This is just the mean of the x squareds minus the square of the mean of the x's. Okay, so that's a function which is going to which will calculate the variance of a list for us. So we do, we've generated a list of 1,000 random numbers and calculate its variance. We do it several times, typically we're getting somewhere around 0.083 or something. If you remember your statistics, you could go away and work out what we really expect the variance ought to be. The variance of a sum of 1,000 uniform random variables. But okay, so let's try and do a faster version. Faster and also just easier and tidier and generally better. Okay, so we're here now. So we're going to do random dot. Sorry, wrong way around. Is this? Check if I got the. Yeah, so I'm just misremembering this. Yeah, so instead of rnd.random, we have to build the NumPy version, right? Yeah, that's the point. So we're going to use the NumPy version of the random number generator, which has a slightly different name. So this was called rnd.random. For the NumPy version, we have to call it np.random.random. But the advantage of the np.random.random thing is that we can give it a number in here. Let's so as we did. Exercise example here. So here we can give it an argument, which is the length of the list we want. So now instead of having to build up the 1,000 random numbers by going through a loop, we do it all in one step. And this is more the same kind of idea as using these universal functions. And then so then we want to do this kind of the sum of the x's and also the sum of the x squared. So if we could do L star star 2, right? So that's going to be the list of all the squares of all the L's, and that's a kind of universal function type thing. It'll be done very quickly. Okay, but then we want the sum of those. Unfortunately, NumPy has a sort of built-in thing to do the sum. We just do L star star 2 dot sum, and then we divide by n to get the mean. And then then we can take the sum of the x's and divide by n to get the average of the x's, and then we square that. Okay, so that's basically the same as thing we did there, but just kind of written in one line. And that's kind of course, this is much closer to how you would write the formula just in normal mathematical notation, and then we're going to return that. Okay, so let's. Okay, so again, you can run this var1 function. It generates 1,000 random numbers and provides the variance for us. Actually, let's. So that's reasonably slick, but let's also just mention that we didn't really need to do any of this work at all. The variance, like all sorts of kind of standard functions, it's actually just built in. So we can just do np dot we sort of generate our list of it's wrong here. This should be an n. So we generate n random numbers like that, and then we just calculate the variance using the built-in variance function. And well, there's a message there. NumPy is a very rich library. It does all sorts of things, and before you wade in and start doing a lot of work to code something up, you ought to just check whether someone's already done it for you. So let's just check what's going on here. It's not printing anything, and so if we look at this, you should notice that we failed to put in a return statement, and that's why it's not printing anything. We calculated the variance, but we didn't return it. Okay, so now if we do that, then again we're getting similar kinds of things. So now let's so now we can run the timer and see how long this takes. Okay, so this is running. It's going to do so this actually did lots of so this %timeIt command. It sort of runs the thing many times to calculate how long it takes. She says here it ran 100,000 loops each time, and did that 7 times over, and it calculated the amount of time it took. So taking about 14 microseconds for each invocation. So let's try doing it with the slow version. So this didn't do. It was a shorter test because it only did 10,000 times each. But here you see it's taking 74 microseconds, about 6 times longer than the fast version. So that's an illustration of why you should always use those kind of universal functions if you can.